Section 13.8, acid-base properties of salts. So salts are going to be ionic compounds. They can be made by the reaction between an acid and a base. When they're dissolved in water, they're going to break up into their component ions, which are going to move about independently and can behave themselves as either acids or bases under certain conditions. So, for example, if you've got the conjugate of a weak acid as part of your base, then, or part of your salt, then it's going to be slightly acidic. If you've got the conjugate base, it's going to be, as part of your salt, it's going to be slightly basic. So salts that consist of the cations of strong bases and the anions of strong acids have no effect on H+ when dissolved in water. So KCl, like from KOH, right? The potassium part here, no effect. The Cl from HCl, which is a strong acid, no effect. So KCl, NaCl, sodium nitrate, potassium nitrate are all neutral and have a pH of 7. Salts that produce basic solutions are formed if the anion, so the left or the right-hand side of the salt, is the conjugate base of a weak acid. So for any weak acid and its conjugate base, remember that Ka times Kb is Kw. And if we take the log of both sides, we get pKa plus pKb is pKw. And so at 25 degrees C, our Kw is 1 times 10 to the minus 14, so pKw is 14, and pKa plus pKb is 14. So if you know either Ka or Kb, you can calculate the other. And that's the same thing we saw by doing, Ka is going to be Kw over Kb, or Kb is Kw over Ka, right? They're just doing the log-based version of that math. So let's calculate the pH of a 0.3 molar sodium fluoride solution. Right? The Ka value of hydrofluoric acid is 7.2 times 10 to the minus 4. This sodium over here has no effect on the pH, right? It's not going to generate H+ or OH- because it's the conjugate of a strong base. Right? The major species in solution are going to be sodium+, F-, and H2O. The sodium doesn't count. HF is the weak acid. The F- ion must have a significant affinity for protons. So it's going to pick up some protons. And the dominant reaction is going to be that the fluoride is going to react with water to form hydrofluoric acid and hydroxide. Right? This is a weak acid, and hydroxide is a strong base. In the fight between these two, a weak acid and the strong base will win. We've got our expression for Kb. We're going to set up an ice table. The value of Kb can be calculated from Kw. So they gave us a Ka value. We're going to find Kb. So we're just going to do Kw over Ka. And we'll do 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 4. And we get 1.4 times 10 to the minus 11. In our ice table, we had an initial fluoride concentration. We're going to assume no concentration that's significant of either the HF, hydrofluoric acid, or the hydroxide. We're going to lose a little bit of fluoride to form a little bit of hydrofluoric acid and hydroxide. So at equilibrium, we've got 0.3 minus x, and x. So plugging those in, we get x squared over 0.3 minus x. Since x is well separated from the initial concentration, right, this 10 to the minus 11 versus 0.3, we're going to assume x is small. And when we solve for x, we get 2 times 10 to the minus 6. It's valid according to our 5% rule, which means that our hydroxide ion concentration is equal to x, or 2 times 10 to the minus 6. We can use that to find a pOH of about 6, 5.69. And so our pH is going to be 14 minus 5.60, which is 8.3, which is basic, which is what we're expecting. So consider the dissociation of hydrocyanic acid in water. If I've got HCN reacting with water, I'm going to form H3O+, and cyanide, and it's got a Ka value. Since HCN is such a weak acid, the Cn minus appears to be a strong base. So we're going to consider the reaction where the cyanide ion reacts with water, where we've got Cn minus reacting with H2O to form HCN and OH minus. Our Kb value is going to be Kw over Ka, and so our Kb is going to be 1.6 times 10 to the minus 5. Cn minus appears to be a weak base because Cn minus is competing with hydroxide for the H plus instead of competing with the water. These equilibria show that the following relative strengths of the base. Hydroxide is stronger than Cn minus is stronger than H2O. What about a salt that produces an acid solution? Well, an anion is not a base, and the cation is the conjugate acid of a weak base produces an acidic solution. And honestly, there's really only going to be a couple of these because you're not going to get a lot of salts where this cation is going to be something that is both soluble and also going to be a weak acid. So salts that contain highly charged metal ions can also produce an acidic solution. The charge on the metal ion polarizes the OH bonds in the attached water molecules. This makes the hydrogen in these water molecules more acidic than those in free water molecules. The higher the charge on the metal ion, the stronger the acidity of the hydrated ion. So we can calculate the pH of a 0.01 molar aluminum chloride solution. The Ka value for aluminum hexahydrate, 3 plus, is 1.4 times 10 to the minus 5. The major species in solution are going to be the aluminum hexahydrate, chloride, and water. Since the aluminum hexahydrate ion is a stronger acid than water, our dominant equilibrium is going to be aluminum hexahydrate is going to form aluminum hydroxide, pentahydrate, because I got 5 of these, and some H pluses. We know that the Ka value is 1.4 times 10 to the minus 5. Our equilibrium expression is going to be our products over our reactants. We'll set up an ice table where we're going to start off with 0.01 molar aluminum hexahydrate, and we're going to start off with no aluminum hydroxide pentahydrate and no H+. We're going to lose some of our reactant to form some of our product. We get 0.01 minus X, X, and X. Plugging those values into the equilibrium expression, we're going to end up with X squared over 0.01, assuming that this X here is going to be small. Solving for X, we get 3.7 times 10 to the minus 4. And that is our H plus concentration is equal to X. So our pH is going to be somewhere around 4, and we end up with 3.43. Right? We can qualitatively predict the pH of solutions in which both the cation and the anion have acidic or base properties. So really what's happening is you've got a fight between the Ka of the acid component that's making H pluses and the Kb of the basic component, the anion, that's going to be making hydroxide. And whichever one of those is bigger is going to control the pH. So if my Ka is bigger than my Kb, my pH is going to be less than 7. It'll be acidic. Right? If they're about the same, right, I'm making as many H pluses as I am OH minuses, it'll be neutral. If my Kb is bigger, my pH will be basic. I'm making more OHs than I am H pluses. It's going to be a basic solution. All right, so let's do a quick concept check here. We're going to arrange the following 1 molar solutions from the lowest to the highest pH. All right, pause, give yourself a second, and let's think about this. Okay, welcome back. So our answers that we're going to do HBr, HF, HCN, NH4Cl, NaCl, sodium cyanide, ammonia, and sodium hydroxide. All right, starting off over here, we've got a strong acid. HBr is a strong acid. Back down here, we've got a strong base. NaCl is going to be pH 7, which is neutral. HF is a weak acid. Right? It's a pretty strong weak acid because it's still in that hydrohalide series, so it's going to be stronger than HCN, which is itself a weak acid. And here we have a salt where this part here is a weak acid, and then this conjugate over here is neutral. For a sodium cyanide, this is neutral. And I've got the conjugate weak base, Ammonia is a weak base. And then, like I said, finally, the sodium hydroxide is a strong base. All right, let's do another concept check. We've got a 0.3 molar solution of sodium fluoride. The Ka for the hydrofluoric acid is 7.2 times 10 to the minus 4. What are just the major species in solution? Okay, they're going to be sodium plus, F minus, and water. Let's predict whether an aqueous solution of the following salts will be acidic, basic, or neutral. So I've got NH4, ammonium, and this guy over here is probably acetate. So I've got ammonium acetate. The two ions in solution are going to be NH4 plus and acetate. The Ka for the ammonium is 5.6 times 10 to the minus 10, and the Kb for the acetate is 5.6 times 10 to the minus 10. Thus, the Ka for NH4 plus is about equal to the Kb for the acetate, and the solution will be neutral. All right, so let's look at some of these pairs. So if the cation is from a strong base and the anion is from a strong acid, so KCl, potassium nitrate, NaCl, it's going to be neutral. Neither the cation is going to act acidic, nor will the anion be a base. If the cation is from a strong base, so we got something like sodium, right? This part's going to be neutral. And the anion is from a weak acid, like fluoride or acetate. The anion will act like a base, and the cation has no effect. It'll be basic. If the cation is the conjugate of a weak base, and the anion is from a strong acid, so I've got ammonium chloride, like from HCl, the cation is going to act like an acid. The anion has no effect. It'll be acidic. Right. If the cation is the conjugate of a weak base, and the anion is a conjugate of a weak acid, they're both weak conjugates, like ammonium acetate or ammonium cyanide. And really, it's like this ammonium that you're looking out for, right? The cation's going to act like an acid. The anion acts like a base, and that's where we're going to see which one's going to dominate. Is it going to be Ka? If Ka is bigger, it's acidic. Is it going to be Kb that's bigger? If Kb is bigger than Ka, it's going to be basic. If the cation is from a highly charged metal ion, and the anion is from a strong acid like aluminum nitrate or iron chloride, the hydrated ion is going to act like an acid, and the anion has no effect. It's going to be acidic.